We've done quite a bit of equation solving already using the trig function. So not only did we do a whole section on solving equations, but we also were looking at the sine and cosine laws, which generally required us to solve small equations, and just kind of talked about a lot about how we get multiple answers for these equations. And looking at the graphs of sine, cosine, and tangent, it should be quite clear that these are not one-to-one functions. If you remember any of your horizontal line tests for one-to-one functions, every single one of these fails. All these horizontal lines are hitting multiple points. So definitely not one-to-one functions. And what that means is that a perfect inverse doesn't exist. So instead, what we look for is what's called a restricted inverse. It's actually the exact same thing that you would have seen that you've definitely used before when dealing with the inverse of y equals x squared. So what we do in this scenario is we restrict the domain of x squared to some domain where it hits all of the range, but it's one-to-one. So for y equals x squared, we restrict the domain to x greater than or equal to 0. And that red portion of the curve here is actually one-to-one. And so the square root function, which is sort of our inverse, it cancels the square perfectly when x is in that restricted domain. So root of x squared is x for x in that restricted domain, but it's not quite perfect for inputs that aren't in that restricted domain. So the inverse, it's not perfect. So if we take, for example, -2 squared, we do not get -2 if we take the root of -2 squared, right? It actually is +2. So the inverses don't work when we're not in that restricted domain. And so what we do is just sort of the exact same idea for sine, cos, and tan. What we'll generally do is define this restricted domain. And the way we will define it is hopefully some connected piece that hits the whole range, the -1 to 1, but is 1-to-1. So for y equals sine x, it goes from -π/2 to π/2. And for cos x, we can't have the same range here because if I chose that, you can see that's not 1-to-1. So we have to choose a slightly different one. So for cos x, it's either actually going to go from 0 to pi. And for tan, we actually can use, oh, sorry, my tans are all off. I just realized these are supposed to be over 2s. That should be, that's π/2. That's just a pi there, 2π/2, if you will. And that's 3π/2. Sorry about that. So for tangent, we can just take one of these little waves. And that one, it will actually be an open interval, -π/2 to π/2, only because it's not actually defined. It's undefined at those endpoints. So those are the restricted domains that we have for these functions. And so basically what that means, what the inverse functions are going to do is map us back into those domains. So we'll maybe do some examples here. Okay, so I've written down a couple of examples for us to try here. We're just going to go over like exactly what these inverse functions mean. For your sake, you can use a calculator for these, so don't stress out too much. But what this means here, cos to the -1 of -1/2. I'm actually going to rephrase the one on the right. Why not use both types of ways of describing these? So cos to the -1 of -1/2, what this means is the angle theta, so that cos theta equals -1/2, right? So if we had theta equals cos to the -1 of -1/2, it's just sort of swapping this equation for its inverse equation, right? The input becomes the output and vice versa. So that's exactly what this means. And so specifically when I say the angle theta, we have to refer to that restricted domain, and that's really important because the inverse function maybe doesn't know what theta it is exactly that you're looking for. All it's going to give you is the angle theta in 0 to pi, right? So that specific restricted domain for cosine, the angle in 0 to pi that has this cosine ratio. And so at this point now we can just sort of use our cast rule to draw this. So if cosine is going to be negative, it does have to be on the left side of the xy plane. But specifically, we want it to be between 0 and pi. So it does have to be across the top. So it's across the top. I can get rid of the bottom. I want cos theta to be -1/2. So that tells me it's got to be on the left side for cosine. So it'll be -1/2. And this should give me my 30, 60, 90 triangle. The biggest length there is the √3, so that'll go with my 60. And so we should be able to find this angle just using all the same stuff that we've done with equation solving. That'll be 180 minus 60, so 120 degrees. And we'll just convert that to radians. So 2 pi over 3. So if you plug it in your calculator, if you have it set to degrees, it should give you out 120. If you have it set to radians, it should give you whatever number is equal to 2 pi over 3. So, but again, you could just use a calculator. You don't really need to necessarily be able to do these graphs. Okay, so arctan of -1/√3. So this is going to be the angle in specifically the restricted domain of tan so that tan theta, sorry, I'm missing the word, the angle theta in there. So that tan theta is -1/√3. So same idea. I want to be in that restricted domain of -pi/2 to pi/2. So that would go from here to here. So it's my right side of the graph. I don't want to use the left. And then I want a negative tan ratio. So that means it's going to go on the bottom. -1/√3 for tan. That means y is -1. I'll have √3 for the other side. My Pythagorean theorem gives me a 2. This should be the 30 angle here. And so specifically for it to be from -pi/2 to pi, I have to go down. I can't go all the way around because it'll be outside of that region. So it's going to go down. It'll be -30 degrees. And so converting that to radians is -pi/6. So that's what the inverses mean. We can't quite do that perfect cancellation. They have a very, very specific meaning.